Hello everyone. Today we're going to learn about an important as well as interesting concept from the subject Computer Organization and Architecture, namely Complete Instruction Execution. This video is presented by Group B1. Now before we move on to understanding the complete instruction execution cycle, there are some prerequisites that we need to be aware of. The first one being, what are registers? Now registers are nothing but type of computer memory used to quickly accept, store and transfer data and instructions that are being used immediately by the CPU. So this is nothing but main memory, except that this data is needed frequently by the CPU. So instead of storing it all the way over in main memory, we've stored it in the CPU itself in the form of registers. So now let us look at some of the commonly used registers that we will be using in the instruction execution cycle. The first one is program counter or PC. This stores address of next instruction to be executed. Then we have the instruction register or IR. It contains actual or encoded instructions. Then we have the memory address register or MAR. This holds address in memory to which data is transferred. Next is the memory data register or MDR. It holds contents found at address held in MAR or data to be transferred to primary memory. So the memory data register contains actual data that has either been found at a particular address in memory or data that needs to be transferred to a particular location in the memory. Next we have the multiplexer or MUX. Now the MUX is a device that allows digital signals from several sources to be routed onto a single line of output. So it does this as it has a data selector lines which specify which input signal has to be switched onto the output line. Next we have the arithmetic logic unit or ALU. This is the part of CPU that carries out arithmetic and logical operations on operands. So operations such as addition, subtraction and multiplication are carried out by the ALU. Another important concept we need to be aware of is the WMFC or wait for memory function completed. Now as we all know that the speed of processor is greater than speed of memory. Thus the processor has to wait for memory function to complete its task and wait for the MFC signal which is sent by addressed device when contents of specific location have been read. Now let us look at the basic operational concept of the instruction cycle. The first thing that we would need to do is to fetch instruction pointed by the program counter from memory to IR. So whatever address is stored in the program counter, we will have to go to that address in the memory and find out the content of that particular location in the memory and send this content to the instruction register or IR. Next we will decode the instruction, then we will fetch the operands if required. Now if our operation says that we have to perform a particular operation on the contents of two registers, we will not need to fetch the operands from memory as they are present in the CPU in the registers itself. Next we will execute instructions and finally we will store the result into memory if required. If not, then we will store them into the registers themselves. Now as we saw in the previous slide, that the first step was to fetch instruction pointed by PC to IR. So how do we go about doing this? To do this, the first step that we will have to undertake is to transfer the contents of the program counter register to MAR. So whatever address is stored in the MAR, we will transfer that to the memory address register and we will generate the read signal. So we will tell the MAR to go into the memory and hunt for this location that was stored in the program counter and check what content is stored at that location. So obviously it will need some time to do this. So while the MAR is performing this task, we will patiently wait for the MFC. Now after we get this signal, the main memory will transfer the data that it has found at that particular location in memory to the MDR or memory data register. So from the memory data register, we will send this to the instruction register or IR. Next, we will decode the instruction. So for example, if we have an instruction saying add R1 and R2, so what this means is we have to take contents of register R1, we have to take contents of register R2, add them and store the result in register R2. So to do this, first of all, we will take the contents of PC and store them into the memory address register. Then we will ask the MAR to hunt for this location and see what content is stored there and generate the read signal. So while it does this, we can do something productive in that time, right? So what we do is we increment the program counter register, because previously we have learned that the program counter register must always point to the next instruction that is to be executed. So while we are waiting for the memory function complete signal, we will increment the program counter by 1. If it is a 4-bit computer, we will increment it by 4. Then next, when the memory sends the data to MDR, we will take it and we will store it into the instruction register or IR. Then we will decode the instruction and finally execute the instruction. Now let us understand this whole process with the help of a diagram. So the first thing that we will need to do is take the content of the PC through the bus and we will transfer it to the MAR. So PC out, MAR in, and we are taking the address, giving it to MAR and asking MAR to find this address and find the content that is stored at that address. So we are asking it to read whatever is stored at that particular memory location. Next, what we will do is, now while we are waiting for MAR to complete its task, we will take whatever is stored in the program counter register and we will store it in Y. Now Y is one of the inputs of the multiplexer and other input is the constant number 4. So these both are the inputs and we have placed the select line at constant 4. So obviously the output A will also be 4. Now here in B, we will again transfer the contents of the register of the program counter register, and now the inputs of the ALU are the constant 4 which is stored in A, and in B we have stored the initial content of the program counter register. Now we will ask the ALU to add them and the answer will be stored in Z. Now from here we will take it out, Z out, and we will store it in PC in, and then we will wait for the memory function completion signal. Now once we get this signal, we will get data which will be stored in MDR. So from here we will take the data out and we will store it in the IR register. Now to the actual addition that we have to do from contents of register R1 and R2. These are our general purpose registers from R0 to Rn-1. So we will take content of register R1 and we will store it in Y. Okay, so from here it will go to the MUX. It is one of the inputs of the MUX, the other is the constant 4, but this time we will select the constant Y, and here we will get the output of the multiplexer as Y. So what content is stored in R1. Next we will take whatever content is stored in R2 and we will store it in B. Now we will ask the ALU to add both of these and the answer will be in Z, so Z in, and lastly we will take this out and we will store it in R1, so R1 in, and that's it. That is the end of the execution cycle. So that's it. I hope this video was helpful and you understood all the concepts. If you like this video, then don't forget to like, share and subscribe, and thank you so much for watching the video.